All right, thanks. So we finished this one. We see that there is indeed a reaction. And, with this method, you don't really have to worry about memorizing a whole bunch of exceptions, except not everything occurs on the chart. That's the problem. And so sometimes we have to use like a hybrid, method. A, B, C, D. I think we're on E, is that right? A hybrid. A hybrid method is, a combination of chart plus other. And so let's look at an example of something like that. An example would be something like HCl plus potassium permanganate, KMnO4 plus ethanol, CH3, CH2OH. And what does this produce? Well, looking at this, some people will say, okay, this looks like a double replacement here. And so, say for example, HCl and KMnO4, AB plus CD, what should that yield? That should yield KCl with HMnO4. What's the driving force for double replacement reactions? Gas formation is one. Precipitation is another. Well, KCl is not a gas. HMnO4 is not a gas. Are either of these precipitates? No, neither. These are group 1. Group 1 compounds are soluble. And then what else? There's one more, and the one more is going from a stronger acid to a weaker acid. And so we're going from a stronger acid, HCl, to a weaker acid. What's the name of this acid over here? HMnO4. Name that acid for me. Name the anion for me. Name the anion. Manganate or permanganate? Permanganate, and so 8, you just change the ending. 8 goes changed to ic, acid, permanganic acid. So this is permanganic acid. Is permanganic acid one of the strong ones that you memorized in Chem 4? No, so you assume it's weak. There are actually stronger acids than the ones you memorized in Chem 4, but they just aren't that common. A lot of people work with them. So. Anyway, so this reaction occurs, but this isn't the main reaction here. This is some kind of side reaction. So let's take a look at the main reaction. Well, that's it for the double replacement. I can't really do anything here. So let's try redox. First step in redox is we need to inventory. And so let's try redox and see. We inventory. When we inventory, we have HCl, which is a strong electrolyte. So it's H plus, Cl minus. KMnO4, is that a strong electrolyte? Yes, no? KMnO4 is actually a strong electrolyte because it's soluble salt. Soluble salt. Soluble salt, salt's an ionic compound. And so this is going to give us potassium and permanganate. Ethanol, is that a strong electrolyte? No. Is it a weak electrolyte? No. Is it a non-electrolyte? Yes. Non-electrolyte. Is it soluble in water? Yes. All these are aqueous. Maybe I should have specified that. These are aqueous. Ethanol is very soluble in water. But this is a non-electrolyte. It doesn't dissociate. So we just consult the chart next. We look for H+. H+ is an oxidizing agent. Chloride. Chloride only occurs on the reducing agent side. Potassium ions only occur on the oxidizing agent side. Permanganate. Permanganate occurs on the, do you see it there? Here it is. Permanganate. Except permanganate needs H+. Do we have H+ present? Because if H+ isn't present, then permanganate's not going to be nearly as reactive. And the answer is, we do. Where's the H+ coming from? It's coming from HCl. And so permanganate in the presence of H+ is there. This just shows a 1:8 ratio, so we're going to get some, excess reagent, limiting reagent type deal. There's no big deal. We have both present. I don't know which one's going to be in excess, which one's going to be limiting, but it doesn't matter yet, because we're going to just do this stoichiometrically. Problem comes with ethanol. Some species that don't occur on the chart because the redox properties aren't significant, and they aren't that common. Like these superacids. Superacids aren't that common. It's just a special branch of chemistry that people work with superacids. So you don't have to memorize them. Well, some of these items don't occur, but maybe ethanol, maybe the redox properties of ethanol are insignificant. This could be the reason they don't put it on the chart. It's insignificant. Ethanol doesn't really participate in redox reactions. Would you agree? No, I wouldn't agree at all. Right. I wouldn't agree at all because ethanol, we know something about ethanol. Is ethanol electron rich or electron poor? Electron rich. Electrons in rich species like metals are flammable, right? In fact, if you buy a jar of metal, powdered metal, there's all kinds of warnings on the bottle saying flammable. Keep away from flame. I should bring some powdered metal and ignite it. Flame. But you got to watch out because those are fuels. Electron-rich species are fuels, right? Why do you think ethanol is not on this chart? One of the reasons why probably ethanol is not on this chart is because all alcohols are highly flammable. Ethanol, methanol, rubbing alcohol. Do you want to put every single alcohol on this chart? No, there are way too many. I guess you could put a class of, alcohols. What about methane? Is methane highly reactive in redox? Yeah, methane is a powerful reducing agent. How powerful? Well, we can get an idea how powerful methane and ethanol are because we try to burn stuff. Do you think it's easier to burn copper metal or ethanol? Copper metal or ethanol? Ethanol is easier to burn than copper metal, right? Try to burn your pennies. So ethanol, I would say, is stronger, right? Is it stronger than iron? Do you think iron ignites easier than ethanol, or ethanol ignites easier than iron? Ethanol. So it's stronger. In fact, ethanol, I would say, is a strong reducer. Maybe not as powerful as like sodium. Sodium mixed with water. If you mix ethanol and water, fortunately we don't get an explosion, so ethanol is not as strong as sodium. So it's somewhere around here, right? In here. And so we can get an idea of certain things just having some factual knowledge about this. Same thing with hydrocarbons. Hydrocarbons are strong reducers like methane, ethane, propane, butane. Those. Same thing with sugars. Can you burn sugar? Yeah, easily. If you get some table sugar, it burns quite easily. But the problem is okay, so we know that ethanol is a good reducing agent, just from our experience with ethanol. It's a good reducing agent. But the problem is what do we do in the next step? We got to pick the strongest reducing agent and the strongest oxidizing agent. And I don't really have this ranked properly. Well, let's start off with the oxidizing agent because that's going to be easier. And we're missing one thing. Do you know what we're missing?
Yeah.
know what we're missing? We're missing water. Water can go both ways. You know, water is a reducing agent and an oxidizing agent. I think I missed water this morning. And this, I don't remember. So we have how many oxidizing agents? 1, 2, 3, 4 oxidizing agents. Can you just look at it and tell me what the strongest oxidizer will be out of that without looking at the chart? Would it be number 1, HCl? Number 2, I mean H plus and H, H plus is coming from HCl, so H plus. Number 2, potassium ions. Number 3, permanganic acid, H plus and permanganate. Or number 4, water. Yeah, permanganate acid. In fact, permanganic acid should be what we call not just a plain old mineral acid, it should be an oxidizing acid. Why? Because of the oxidation state on manganese. Manganese is a full +7 oxidation state, which is huge. So this is going to be the strongest oxidizing agent. Can you figure out based on this? Let's compare chloride with ethanol. What's easier to burn? Chloride, like in sodium chloride? You run out of wood, throw some sodium chloride. Will sodium chloride combust by itself? If you tried to ignite it with a flame, would it stay lit and start to burn? No. And so ethanol is going to be better. How about water? If you tried to ignite water, would it stay lit and burn? No. And so for sure, ethanol is going to be the best reducing agent. Sponge, because if you try to ignite ethanol, it's going to stay lit. You can remove the flame, and it'll burn. All right, so we just consult the chart, and then we write out the reactions. So, this is just copying. So we look at permanganate, and I look at that over here. I just copied off the chart here. No, that's not permanganate. This is permanganate. And so I get permanganate plus 8H plus 5 electrons produces Mn2 plus 4 H2O liquids. Then I look for ethanol, but there's a problem. The problem is that, what is the problem? The problem is ethanol doesn't occur on the chart. So unfortunately, here's where the elementary student would, actually they would have gotten stuck with ethanol, but here's where we kick it up a notch in difficulty, because we don't have this. You know what these are called? These are called half reactions. Half reactions we can get from the chart, or potentially we could get half reactions from what? Balanced half reactions. We can get from the chart, just copy it down, or we could get it from where? 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 Chemical equations? Sort of, yeah. Where else can we get half reactions, balanced half reactions from? This is the whole thing. The whole thing is about making connections. The way you guys can make connections is you see something repeatedly. You see this chart a whole bunch of times, then, obviously it's going to be pretty easy to use this chart, and you kind of remember things from the chart. Which species occur on both sides. Several waters, which water to use. On tests, people come up to me, there are 2 waters here. Which one should I use? I don't know. Use whichever one you want. I do know, and I'm not going to tell them, basically. But you try to make these connections. If you make the connection, then the problem is not that hard. And so ethanol, we need the half reaction for ethanol. And so when ethanol is oxidized, what does it produce? Well, did I tell you about my Joshua Tree wine purchase? Yeah, when the ethanol is oxidized, it can produce acetic acid, vinegar, under mild conditions. But that's tricky because what are mild conditions? And what do you think about permanganate? Permanganate and acid. Permanganate and acid, is that mild or is that a pretty powerful oxidizer? You think permanganate in acid is mild or pretty powerful? Pretty powerful. More powerful than oxygen? More powerful than oxygen? More powerful than oxygen? Yes. What happens when oxygen oxidizes ethanol? Well, when oxygen oxidizes ethanol, you can form different things depending on the condition. When oxygen oxidizes ethanol, you can form soot, if there's not enough oxygen. You can form carbon monoxide, or you can form carbon dioxide. In fact, when you can do combustion of organics yields CO2 and water. What about carbon trioxide? Because this is an even more powerful oxidizer than oxygen. Can't we form carbon trioxide, carbon tetraoxide, carbon pentoxide, carbon hexaoxide? You got a more powerful. In fact, this is significantly more powerful than oxygen. Here's oxygen. Here's permanganate. Permanganate is way stronger. And so that's going to oxidize the heck out of ethanol and create carbon trioxide or carbon tetraoxide. Yes or no? No, because those don't exist, really. And so the only product that makes sense here is that the ethanol gets oxidized to carbon dioxide. Yeah. Well, that's not balanced. That's not a balanced half reaction. How do we get a balanced half reaction from this? We have to this is called what? In order to balance this half reaction, we have to use what method? Skeleton redox. Good. And so we already did this one. We did this. Actually, we did the whole thing. We did the whole thing except, when you're doing skeleton redox, we could have skipped balancing this because we could have just copied it off the chart. It's the exact same, right? And so that would have saved you time. This we would have had to do. Because you have the chart, you could save a little bit of time and you don't have to balance it if we have permanganate goes to Mn2+, right? It's right there, the balanced half reaction. And so this is a hybrid between, the chart and skeleton redox, right? Where we just use our factual knowledge to predict that, alcohols, hydrocarbons, carbohydrates, even carboxylic acid should be oxidized ultimately to CO2. Your body does this. You consume vinegar. You consume vinegar, eventually it's not burned as in the flame, but it's burned as a redox reaction. You're going to produce energy, and vinegar is going to get oxidized to CO2, right? Carbohydrates get oxidized to CO2. Alcohols, don't drink methanol, but if you drink ethanol, that's eventually going to be converted into CO2. And so in the body, if you take biochemistry, it's all redox reactions. There are lots and lots of redox reactions. Not everything, but a lot of it. So we already figured this one out, etc. The rest of it can be the same as we did before. And so this is kind of a hybrid method. You know, ethanol, like methanol would have been the same, you know, whatever. Sucrose. Those we should be able to figure out. All right, those are the redox reactions we're going to look at. We're going to move on to the next category of reaction. Next category of reaction will be acid-base reactions. With acid-base reactions, we have two types of acid-base reactions. We have Bronsted-Lowry. So acid-base, let's just say this is category 2, I think. 1. Bronsted-Lowry. Bronsted-Lowry reactions are just proton transfer. The acid is the proton donor. The base is the proton acceptor. Proton donor, proton acceptor. So Bronsted-Lowry, the way we figured these out is very similar to what we did for redox. So let's look at a particular reaction here. Example reaction we're going to do is this. What's the name of this? Sodium phosphate and this. The potassium bisulfate. When I look at this reaction, it looks like a double replacement. It looks like double replacement. So let's take a look at this reaction here. If it's double replacement, what forms? Well, it's AB plus CD, and so it's going to form what? We're going to form potassium phosphate and sodium sulfate or sodium hydrogen sulfate or sodium bisulfate. Sodium bisulfate. Then we need to balance this. We'll need 3 of these and 3 of these, and then it's balanced. Is there a driving force for this? 1, we look for precipitate. Precipitate? No precipitate, because those are group 1 salts. Group 1 salts are soluble. No precipitate. Are either of those gases? No. Are we going from stronger acid to weaker acid? No. So there's no driving force. This is NR. But this is NR for double replacement. What other types of reactions should we look for? Well, no, it's NR only for double replacement. And so what we might be tempted to do is look at redox. Let's try redox and see. If we try redox, we'll inventory it. And so sodium phosphate, strong electrolyte? Yes, no? Yes, sodium ions and phosphate ions will be present. Potassium hydrogen sulfate, strong electrolyte? Yes. So what does it break up into? Potassium ions and hydrogen sulfate. That's good. That's correct. Why doesn't the hydrogen sulfate break apart? Shouldn't the hydrogen break off from the sulfate? No. The hydrogen does not break off from the sulfate because hydrogen sulfate is not a strong electrolyte. It's not a strong acid. It's what we call a weak acid. Weak acids only partially dissociate, so we leave it alone. So this is that. And water. And so we go down the list. You know, sodium ions are oxidizing agent. Phosphate is not on the chart. Potassium ions. What about hydrogen sulfate? Hydrogen sulfate, well, we go down the list here and we see something that kind of looks like. Wow. Let me get a different one. If we use the chart in your book, I should probably bring up your book. You might see it, but we'll just use this chart here. I see sulfate. Would sulfate and hydrogen sulfate behave similarly in a redox reaction? Sulfate and hydrogen sulfate react similarly in a redox reaction. Pretty much essentially the same in a redox reaction. Yes or no? Can't tell. What do you think? Sulfate and hydrogen sulfate react similarly? No? They're different? No or yes? You have 50-50 chance. What are you going to cross? Yes, they'll react similarly. No, they won't react similarly. What's most important in redox? Behavior. What's most important, this is where we're going to get into structure and other stuff, but they should react similarly. Why? Because sulfur has the same oxidation state in both, +6 in sulfate and +6 in hydrogen sulfate. This hydrogen is actually attached to an oxygen, not to the sulfur. It's going to lower the charge. And so here we have sulfate. We have sulfate, but this sulfate needs something a little more. You know, that sulfate we have in hydrogen attached there, but this sulfate needs strong acid. Do we have strong acid, H+, present here? We got this H attached here, but do we have H+ present? No. And we need a lot of H+ because we're going to form water. And so in this case, it's not going to react the same as sulfate here. And so this is missing H plus. This is going to be an oxidizer or reducer, we've seen before. Phosphate, what do you think phosphate is? Is phosphate going to be an oxidizer, or is it going to be a reducer, or is it going to be both? You think phosphate can go both ways? Turns out phosphate cannot go both ways. Why? Phosphate's only going to act one way. What way is that? What's the oxidation state of phosphorus? +5. That's the same as nitrate. So phosphate and nitrate, nitrogen and phosphorus in the same family. Phosphate and nitrate should be the same, right? Powerful oxidizer. They're both +5. Can it go +6? Do you think phosphate can go +6? Why not? Why won't phosphate go +6 for phosphorus? I just want to throw on another oxygen on there. Rather than PO4, let's go PO5. PO5. PO5 3 minus. +6. Yeah? No. So phosphate is +5, nitrate is +5. Nitrate's a powerful oxidizer. Phosphate should be a powerful oxidizer too, right? No. If phosphate's a common chemical. And so if phosphate were a powerful oxidizer, then it should occur on this chart. This is a chart of common oxidizers. But since phosphate doesn't appear on this chart, that tells me something, by inference. I can kind of infer that the phosphate must not be all that powerful. Because if phosphate were powerful, it should be here, like nitrate. You see nitrate here? All right, so, nitrate's a common chemical, phosphate's a common chemical, phosphate's in detergents and that kind of stuff. Nitrate's here. This is upside down, shoot. But phosphate's not here. Nitrate's here, but phosphate's not here. Okay, that's one thing that makes me think maybe I can ignore phosphate. The second thing that makes me think maybe I can ignore phosphate is there's something missing too. What would be missing? Look at nitrate. What does nitrate mean? H+. And so, this species is missing. A more comprehensive table, you probably could find it, but probably the main reason it's missing is this. It's not very reactive in redox reactions. Otherwise, if it were very reactive, phosphate's such a common chemical, it should be up there. Does that make sense? And so, and plus we don't have any acid, and so we're going to ignore this. We're going to ignore this, and then pick the strongest oxidizer and reducer. The strongest oxidizer is water. The strongest reducer is water. And is water going to react with water in a redox reaction? I'm going to save time here and say no, because if water reacts, let's say this water reacts as a reducer, it forms oxygen gas. See that? If water acts as an oxidizer, it forms hydrogen gas. And so do you think the formation of oxygen gas and hydrogen gas from two waters reacting is favorable? No, so we're just going to skip this for the redox. And so instead what we're going to do is we're going to look for acid-base. Water's stable, it's not going to undergo redox between two species there. And so when we look at acid-base, we consult the chart. And so the first is inventory, which we did. The second is we consult the chart. Consult chart. And so rather than a redox chart, we're going to be looking at an acid-base chart. I'll just do that. Let me show you acid-base chart real quick. This is an acid-base chart here. The same thing, we don't have two separate charts. We don't have one chart for acids and one chart for bases. We have a chart for both. And we have a chart for both because a strong acid means its conjugate is very weak. So HI is a strong acid because it loses the H plus easily. That means iodide doesn't really grab onto the H plus. So iodide's got to be a very weak base. And so we got the conjugate relationship here. And so we just need one chart. We go down the list and look. So if this is our inventory, let me just do this really quick. If this is our inventory, we look at the acid-base inventory. Sodium ions are neither proton donors or proton acceptors, so those are neutral. Phosphate is a base. In fact, phosphate is borderline strong base. You know, if you look at phosphate over here, it's right on the border. Phosphate, and the next one is hydroxide. So it's a pretty strong base, but we still call it a weak base because it's not stronger than hydroxide or equivalent. Potassiums are neutral. HSO4 minus is amphoteric. It's both an acid and a base, but it's a much stronger acid than it is a base. In fact, its base properties are so weak, a lot of people ignore the base properties of HSO4 minus. H2O is both an acid and base, but it's equal. You know, it can go either way equally. And so the procedure is the same. What we do is we write down the equation, you know, and add them together. Adding them together is easier because, you know, there's only one proton transferred. Only one proton. Whereas in redox, you know, we could have 1 to 5 electrons in the half reaction. Here we always have one proton, so we never have to multiply. All right, unfortunately, we're out of time, so continue next time.